Okay, so in the last few classes we have been looking at the fully differential op amp. So this was the simple fully diff amp we considered. So as such, the circuit is complete or something is missing here. If I wire the circuit up like this, will it work or something is missing? Huh? Sorry? Yeah, so how do I set the bias here? No, but it's a fully differential case, so what were we doing? I mean, this is what we have been seeing in the last couple of classes, right? I mean, what is the drain DC potential here? What is setting the DC potential here? No, how is this setting this voltage? No, there is no, I mean, you are setting this voltage, but what about this voltage? What is setting this guy? Come on guys, this is what we have been looking at the last few classes, right? So what is setting this voltage here? Is it voltage set? Is the drain voltage? What is the DC potential here?
VDD minus.
Why? I mean, this is VDD, okay. Why is it overdrive? Overdrive is the gate to source voltage. What is the current flowing here? If this is I naught, this current is I naught by 2, but who is fixing this current to be I naught by 2? But this is a separate current source, this is another current source. How can they be equal? This is what we have been looking at, right? See, we have two current sources here. Come on, people. See, this is a current source setting this current to be I naught by 2. Here I have another current source, nominally should be at I naught by 2, but I can't guarantee it. So what will happen if these two current sources are not equal? If let's say the PMOS current source is not equal to the bottom current source, what will happen to the DC potentials here?
It will go to VDD or 0.
0. So what do we need to do?
So we need to ensure the should be I naught by 2.
Yeah, how do you ensure that?
Negative feedback we use.
What is it called? Huh? What did we call the negative feedback loop? I mean, so what do we have to do?
Like there are 6 concepts, 5 or 6 concepts.
Yeah, so what do we have to do in words?
Take average of this and something like average.
Basically, you have to average the two and set the average to some voltage here, right? And this was called the common mode feedback loop. Okay, that's fine. And we are seeing, I mean, we saw few variants here. So what do we need to do? First thing, in the common mode feedback, what do we have to do?
Take average of this.
First we have to sense the average or sense the common mode. And how can we sense the common mode?
Take resistors to our semiconductor.
We can basically take two resistors here and do this. Or then we saw this resistor could load the output. So what else can we do? What did we do to avoid loading?
Yeah, like one time like buffer also.
Yeah, you can put a source follower here and then have the two resistors like this. Okay. And if you recollect, we also saw you can take average using two MOSFETs directly, where you connect VOP, VOM here. Right? Now, after sensing the common mode, what do we have to do next?
You have to compare it with the reference.
You have to compare it with reference and then control one of the current sources, right? I mean, see, please remember that the issue is because we have two current sources here that are biased independently. We can't have both of them biased independently to the same voltage, same current. So you have this set to some current and make this equal to this current. Okay. So the next step is to go and control the current source, and of course you can either do that by see, one way is, we saw, right, we could directly connect the common mode connection like this. In that case, the common mode is set to some process parameters like gate to source voltage and so on. I mean, one case where we saw was this was directly connected to the gate voltage. In that case, the common mode was set to some source to gate voltage and so on. Or you can go and compare with some reference and then set the current. And for this, we could either use a separate OTA, or in the last class we saw the notion of replica biasing. We can use either of this. Okay. Now, although I have shown this only for this simple diff amp, even if there is a cascode, the idea is the same. So the cascode transistors will come here. The principle is still the same. Now we just need to set the bias voltages for the cascode. That you know how to do, and we also discussed when we are looking at cascodes. Okay. So this is with the single stage OTA, and next we will look at two stage OTAs. So let's say this is my first stage. I need to add a second stage here. What could be my second stage? What can I use as second stage? Common source. So PMOS or an NMOS? Why? Again, you know, right? I mean, if I use a PMOS here, the DC potential here will be more suitable. Okay. So I'll take a PMOS here. So in the other side also I'll have another PMOS. Both these gates are connected, right? So I mean, if I have to draw it at a block level, this is what we have. We have differential OTA, and we have one other differential OTA like this. So let's quickly draw the differential mode half circuit. So the first stage, again, all these node voltages are 0 in the differential mode. So the first stage is a simple common source, and second stage is also another common source. So we have something like this. This is the first stage. And the second stage. That's all. Okay. Again, if you show it at a block level, we'll have something like this. So this is say minus GM1. GM2. And then we'll have their corresponding output conductances and capacitances. So now, will it work like this, or do we have to do something here for the differential mode circuit to work? I mean, let's say I take this and put it up, forget about the common mode. In the differential mode, is it fine, or do we have to do something? I have two-stage op-amp. So if I directly connect two stages, will things be fine, or do we have to do something? Yeah, we have to do some compensation, right? Because as such the phase margin might not be good. So what can we do for compensation? Around the second stage we can put a Miller cap, right? So, and I'll also add that zero cancelling resistor. So this is how it will be. So in the full circuit, where will I have this capacitor and resistor? I mean, I have two second stages. So around each of them, I'll have to go and put it. Okay. So this will set the differential mode. Now what else is pending for the complete circuit? I mean, it's again a fully differential op amp. So if I connect it like this, will it work, or do I have to do something? I mean, now I have looked at the differential mode, right? So in the differential mode, circuit is fine. So what else I have to do? I have to set the common modes, right? Because I have the same situation here. We have two current sources in the first stage. Same is happening in the second stage also. Okay. So as such, you cannot say what the common modes of the second stage as well as the first stage is. These two, I mean, these two voltages or all these four voltages are undefined as such at DC.
But ultimately, can't we set this and this?
Yeah, these two might be equal, but what the absolute values are is we don't know, right?
If we set the middle ones are equal, then this will be equal, right?
But I mean, again, here you have the same situation, right? See, you might set this voltage to something, that's fine. So that is setting this voltage. So that is setting the current in this transistor. But this current need not be equal to the current here, isn't it? Is that okay? Fine? I mean, the point I am making is, as such, the absolute DC potentials at all these 4 points, they are undefined. Okay? Because the situation is similar, we have two current sources in the first stage as well as in the second stage, and the two current sources are connected like this. So if these two guys are not equal, this voltage can go to VDD or ground. Okay. So again, we'll have to have a separate common mode feedback for both the stages. Okay. So let's say I take this first stage, put a common mode feedback and set it like this. So let's see how we might be setting the common mode for the first stage. So again, first in the common mode feedback, what is the first thing we have to do? We have to sense the common mode, and we know we can either use a resistor directly or you can use MOSbased. So what are the issues with using a resistive common mode detector? Loading. What is the issues in using a MOS-based common mode detector? Swing, right? Because the moment you introduce a MOS transistor, that is going to limit the swings. So here, what do you think might be a reasonable choice for the first stage? Why? Okay, let's see. I mean, the issue. What is the issue with using a resistor?
Loading.
What will loading do?
DC gain.
It will reduce the DC gain. So in the two-stage OTA, which stage is contributing to the bulk of the gain?
The middle one.
First stage, right? I mean, if you recollect, one of the reasons for using the second stage, why did we go for a second stage? I mean, why can't
to drive the load?
What kind of load?
Resistive
load, right? I mean, the idea was if I have a high gain here, I can't drive a resistive load because that will load, and that is why we decided to have a second stage. right? So as such, the bulk of the gain is coming from this guy, and this is giving only a modest gain. So if that is the case, do you think having a resistive common mode feedback for the first stage is a good idea? No, right? Because the moment I put a resistor, that is going to load my first stage and reduce its gain, and I want maximum gain coming from the first stage. So I don't want to unnecessarily load the first stage. So looks like having a resistor is not a great idea. So we could use a MOS-based common mode detector. But what is the issue with MOS-based common mode detector? Swing. So is it fine here or no? So let's say I form a fully differential op amp. Take the fully differential OTA and make an inverting amplifier like this. Okay. Now let us say my output here is swinging to some, say, delta V max. So this is basically the output of the second stage, right? The final output. If my second stage is swinging to maximum of delta V max, what can you say about the swings in the first stage?
By 10.
Yeah, but why by 10?
Assuming that the gain of this one.
Basically, it's divided by the gain of the first stage, right? So first stage, it will swing to some delta V max by the gain of the second stage. So do you think the output swings will be large or small here? It is small. Okay, so it is okay to use a MOS-based common mode detector here, because the swings at the first stage are going to be very small compared to the final output swings, and also we don't want to load our first stage. Okay, so here we could use a MOS-based common mode detector. Now the second thing is to see how we are going to control this current. That is, either we'll set it based on some VSG, or we want to set it to some reference. So let us say I want to set it to some reference VCM1 ref. So do you think I can choose any value for this VCM1 ref, or choosing this value will constrain something else? If I choose, let's say this is VCM1 ref, the output common mode is set to what? No. If I give this VCM1 ref as the input to my CMFB, what is the output common mode set to? The same value. So this output common mode, is it also controlling something else?
The input to the.
It's going to the input as the second stage. So what will that decide?
The current of that.
It's going to decide the current here. Okay. So remember that when you will be designing your OTA, you will find that, let us say this is some transistor M5 and M6. So let's say this current, you want this to be at some I5. From your design specifications, let's say you derive this is what you want. So you can't arbitrarily choose your VCM1 ref. You have to make sure that this VCM1 is such that the current in the second stage is I5. Is that okay? So how can I, now I need to generate a voltage VCM1 ref that when applied to the gate of this transistor M5 results in a current of I5. How can I generate such a voltage?
Apply this base of gate of this of M6 and direct to CMFB.
No. Gate of M6 to CMFB. No, I'm not saying that. Let us see. Oops, what's happening here? Okay, probably have to close and open. So what I'm asking is, see, we need to for the first CMFB one, we need to supply this reference voltage VCM1 ref. So how can I generate this voltage VCM1 ref and apply to the first stage? And we saw that this voltage can't be an arbitrary value. It should be such that when I apply this voltage to the gate of M5, it carries a current I5. So how can I generate such a voltage? Okay, I take another MOSFET. What kind of, what MOSFET should that be? PMOS. Is there something specific also? Gate and drain connected and pass the current I5. And other things, this should be identical to M5, right? So now if I pass I5, this is going to generate the required voltage.
Why did we short
This way we will get the required gate voltage to sustain the current I5. Is that okay? So this is how you will have to generate this guy. Okay. So now this sets the common mode for the first stage. Now the second stage is still pending. So let's quickly see that. Okay, again for the second stage, first let's decide what kind of common mode detector we'll use. So with all these understandings, now tell me, will I use a resistive common mode detector or a MOS-based common mode detector?
outside one, right?
Yeah, for the second stage.
Resistor.
Why?
Because after loading one, you can use resistor.
Why?
It is driving the load.
Yeah. Basically, the issue, first of all, we can't use a MOS-based common mode detector because this is going to be having maximum swings. Now, the only option we have is to use a resistor, but the resistor could load and reduce the gain. But if you remember, this was already designed such that it can drive a load resistor. Okay, so you can easily choose my common mode resistor RCM to be large enough than my load and get away with it. Whereas it might not be easy to do that for the first stage because here I've used a normal first stage. I could use a cascode here also for the first stage, right, to have a very large gain. In that case, the output impedance is going to be really large, so it might not be practical to have a common mode resistor larger than this output resistance. Okay, whereas here I know that the second stage is going to have a modest gain, so I can use a resistive common mode detection here. Okay, so let me do that then. So what I can do is I'll take the two outputs, sense the common mode like this, and then I'll have to compare this common mode with some VCM ref 2. Okay, and what do you think could be a reasonable choice for VCM ref 2?
VCM ref.
Why?
Both branches are similar, right?
No, right? Because
and MOS down.
why are they similar? Here we can set VDD by 2. It's output common mode, right? See, even otherwise, so let us say I call this output V0. What is the maximum output I can have? Huh? No, to make sure all transistors are in saturation, right? What is the maximum output swing I can have? This is the swing limits, right? What is the maximum I can have, minimum I can have?
Maximum was like
Just this stage, right? What is the maximum this voltage can go?
VDD minus the overdrive of 5.
5. Okay, this can have a minimum of 1 overdrive, that's all, right? So similarly, what is the minimum I can have here?
Overdrive of 6.
Overdrive of M6. Okay, so let us say both overdrives are chosen to be equal for simplicity. So if this is my 0 to VDD, at the top side I am 1 overdrive lower, bottom side 1 overdrive higher. So this is the range in which I can operate, right? So my output can only swing like this. So here what do you think is a reasonable VDD by 2, right? So that's why it makes more sense to choose this to be close to VDD by 2. So I'll do this and control my current here. Okay. Now as we saw, if you draw the common mode equivalent, this is going to be a first stage this is going to be one stage, and this guy is going to contribute to second stage of my CMFB. So this is looking like another two-stage OTA, right? So what do I have to do? To second stage? I mean, first of all, tell the problem, right? I have, if I draw the common mode half circuit only for the second stage CMFB, this is a OTA, single stage OTA, and the output is connected to this guy and then taken here. So you basically have two stages. So what can you comment about the phase margin as such? It might not be so great, so we have to compensate. So how will I compensate?
Second stage.
So this is my second stage, right? So input and output. So across the input and the output, I'll go and put capacitor. Okay. So this is, let's say, CCM6 or CCM2, to signify that this is the common mode feedback compensation capacitor for the second stage. And we also saw here you might have to have this capacitor here to add a 0, basically to tackle any parasitic capacitance at this node, right? Okay, so one last thing. So this OTA here, what kind of an input stage I can use, NMOS or a PMOS here? Yeah, so again, the space here. See, again, the choice is made based on where the first stage is connected to, right? So here the first stage is connected to an NMOS. So the output stage of my first stage is should be an NMOS, right? Only then these two voltages will be compatible. So which means my input pair must be a PMOS. Something like this. Okay. So this should be a PMOS input OTA. So similarly, what about the OTA you might be using here? This should be an NMOS input pair or a PMOS input pair OTA? It should be an NMOS because the output is connected to a PMOS. Okay. This should be an NMOS input. So I mean, this is the complete two-stage fully differential Miller OTA, right? I mean, again, you can clearly see that I don't have enough space to draw the complete schematic in one page. Okay. So I mean, so it adds no value if you try to memorize circuits. So you should. That's why I'm emphasizing on synthesizing circuits from scratch, right? So only if you understand that, you'll know the functionality of each of these blocks, and then you'll be comfortable to actually draw the circuit yourself or make it yourself, right? Cool. So this is a two-stage Miller op-amp. Now for compensation, along with, I mean, other than Miller compensation, what is the other technique we know? Feedforward. So let's quickly do that also. I mean, in fact, we didn't look at it at a transistor level. We looked at it only at a block level. So let's quickly see its transistor level implementation. So at a block level, we have basically this. So let's say I have one GM, two stage like this. What do I have to do to compensate in feedforward?
Forward.
I have to add a fast path using another GM. Okay. And this GM should be plus GM or minus GM. How is it decided?
Plus.
Why?
Total is like no sign. Down path is.
There should be no sign change. We need to have an LHP 0. and that is possible only if the signs here are same. Okay, so in the two-stage path we have a non-inverting case, so here also I should have plus GM3, right? So how can I add this third GM3 here? I mean, I have GM1, this is GM1, this is GM2. Now to compensate, I need to have the third GM3 connected from the input to the output. So can you suggest me what can I do? What is the simplest GM you know?
Positive GM.
No, I mean not implementation of a GM. What is the simplest implementation you know? Common source. So let's say you take an NMOS transistor. This is a GM. So where do you think its input and output must be connected now?
Input should be connected to the V2 point.
Input must be connected to the actual input. Input of the first stage is my actual input V in. Okay, and output?
Output of M.
Final output. Okay, now you tell me the, I mean here let us say I have marked everything. The inputs are V1, V2. So let us say this is VO1M, VO1P. So this is basically VOP. So tell me if this is V1 or V2 and this is VOP or VOM. I mean, let's say, okay, I'll do the other way. So let us say I decided to connect it to VOM like this. So this should be V1 or V2. Why? See, basically again, we need to have a, first let's see here, right? We need to make sure that the path from the input to here and this to here must be the same. There should be no sign change. So from the actual input, let's say if I increase this, what will happen to this?
Decrease and increase.
So first of all, what will happen to this voltage?
Decrease.
It will decrease. So VOM will increase. So here what should I connect here? If I directly connect V2, if V2 increases, this will decrease. Okay, so what should I connect? V1, right? Because V1 will be the inverted of it. So here I will have to connect V1. Is that clear? So similarly at the other side I will have to go and connect one more GM. So let me make space here. So here I will have to go and connect one more GM whose input is connected to V1, sorry V2. Okay. Now this is the simplest implementation you can have, but if you look carefully, see if I take a fully differential OTA, what can you say about its common mode rejection? How do you want it to be? No, it should be infinite. It should not, basically what it means, if the inputs change in the same direction, neither of the outputs should respond to the change, right? Output should be same. Okay, now let us say when we didn't have this additional feed forward path, if let us say both the inputs change in the same direction, what can we say about these voltages? Will they change or they will not change? If let us say when we didn't have these transistors, right? What I'm saying is, in that case, if the two inputs change in the same direction, what will happen to these voltages? I mean, so how will you find it? How will you find it if it is changing or not changing? You draw the common mode half circuit and do. I mean, or otherwise, let us say this is biased at a constant current I0. Okay. So if both V1 and V2 increase, what can you say about the currents in the transistors? I mean, when let's say V1 was 0, right? What can you say about the currents here? There is no small signal. What can you say about the currents in the transistors? Total current. If there is no small signal, this is what it is, right? And if this is biased at a constant current, the sum of the two currents here has to be I naught. Okay. So now let us say I increase both V1 and V2. Then what can you say about these currents? Okay, you are saying they'll increase. So if this increases to some delta I and both of them increase to delta I, so what can you say about delta I then? It has to be 0, right? I mean, only if one increases and other decreases, then you can have I naught by 2 plus delta I and other can be I naught by 2 minus delta I. Then KCL is valid, right? The moment you fix it at a constant current, the currents in these two branches is set to I naught by 2. So what can you say about the common mode response here? If both inputs increase, what can you say about the outputs here? Okay, we just saw, right, the currents, will they change or not here? Will the currents change? If the currents don't change, what can you say about these voltages incrementally? They will not change, right? I mean, you can draw the common mode half circuit, right? You have, in the common mode half circuit, you have this guy, okay, and then NMOS transistor, and then the bottom current source. Let us say this is an ideal current source for now. If this is an ideal current source, what can you say about this voltage? If I make any change to the voltage here, nothing will change, right? This is the common mode half circuit. Okay. So when we didn't have these transistors here, it is clear that if I make a common mode disturbance, the outputs don't respond. So now let us say I have added these two additional transistors. If let us say V1 increases and V2 also increases, let me clear the space. So V1 and V2 increase. So obviously these voltages don't change. But we have also applied V1 and V2 to these transistors. So now do you think the outputs will change or not change? The final output. So if V1 changes by some delta V, what can you say about the incremental current here? GM delta V, right? Because there is nothing fixing that current. Here also it's going to be GM delta V. So that current will flow into the output impedance here. Yeah, it will take away. It's minus GM delta V. It's okay. So the point I'm making is, now if the outputs change in the common mode fashion, we will have incremental currents flowing due to GM3, and that will flow into the output impedance whatever you have here, and the output will change. So is this good or bad? We have a common mode disturbance and looks like the output is responding to the common mode change. So is it good or bad? Bad, right? So CMRR will be poor. So looks like this is, although differentially this is doing the compensation, it is killing us in the common mode case. So instead of connecting two GMs like this, what can you do?
Another one stage OTA.
Yeah, what do you mean another one stage OTA? Okay, or to start with, see, in this stage, looks like even if I change the inputs here, the outputs don't change, right? What was making the outputs not to change? Huh? This guy was fixing the current in the transistors to some constant value. I mean, if you think about it, this is what is giving common mode rejection here. So what do you suggest now for GM3? I mean, instead of having two transistors like this, what can I do?
Apply the same configuration of the below of the OTA. Like connect the sources and.
So I can put like this and fix its current here. Is that fine? I mean, basically, the way I have drawn it here, these are pseudo differential GMs, right? Without any common mode rejection. The moment I add a current source fixing its current, we get a common mode rejection, right? So that's what we'll have to do. So what I'll do, I'll redraw this slightly. Let me first copy this. So I'll redraw this slightly. I'll separately draw the second stage. This is the second stage. Okay, so let us say this is VO1P, VO1M. Okay, and this was, let us say, VOP and VOM. Or okay, this is connected to some bias voltage here. So now I'm going to add the GM3 and I'll add it like this. Okay, so to VOM what is connected? To VOM I'm connecting V1, so let me mark that. V1 and V2, right? So now let's say this carries a current I2 and this guy carries a current I3 DC. What is the DC current flowing here? I2 minus I3. So what do you think is the role of this transistor here? I mean, let's say when we didn't have the third GM, right? What was the role of this transistor?
Source follower.
No, it was not a source follower. Let's go back to the circuit here. What I'm asking is, in the normal two-stage OTA, what was the role of these transistors? So in the second stage, which transistor is providing the GM here? NMOS or PMOS? PMOS. What is the role of the NMOS here? These two guys. It biasing with a constant current, right? So, but here if you think about it, we already have this current source setting the current here to I3. So I don't need to have this additional current source here. See, other simplest way to think about is, now looks like this current is I2, this current is I3. The simplest choice is to take I2 to be equal to I3. That's a valid choice. That will make the current in this branch to be 0. So which means I don't even need to have this. That's a redundant current source. Okay. So what you can do is you can get rid of this guy and say the two currents are equal. Okay. So if this is some I2, this is also some I2. So this will be 2 times I2. So this technique is often called current reuse, wherein we are reusing the same current for biasing both the second stage and the feedforward stage. Okay. So now I will clean up the circuit and draw it neatly. So what we have is this. So this is V1 and V2. That's all. Okay. So that's all. So now the full circuit is complete. Okay. I mean, I was earlier I was drawing the same thing like this. I just redrew it. Okay, right? So now we'll have to do common mode feedback. So again, for the first stage, I'll put a CMFB. We saw what kind of configurations will be fine. The same things we saw for Miller op-amp will work. So similarly for the second stage, I'll have to do one more CMFB. Okay. So one thing to notice, see, in the first stage, I could actually control either this current source or this current source. Either of them will work. Okay. Now in this second and third stage combined, I have again two current sources, this guy and this guy. What is setting the current in the NMOS here? This current source is setting the current in the NMOS. Okay. So I can control the current in the NMOS transistor by controlling either gate or source of this guy. Now what is setting the current in the PMOS? Output of the first stage. So it's not possible to go and change the output of the first stage, right? Because I even have small signals there. So in this configuration, you can only control DC current of the NMOS. Okay, so again the common mode feedback will be the same. I will have a resistive common mode detector. So I will compare it with some reference, say VDD by 2. Go and do this. Now again for the common mode picture, we have a single stage OTA, and then we have one more transistor here, and the output is taken here. So it is again a two-stage OTA here for the common mode feedback. Okay, so we'll have to compensate this once again for the common mode stability, and for that, what do you think we should do? For compensating, what should I do? Yeah, so I'll have to add a capacitor between the input and output of the second stage. So this is the input of the second stage, and where is the output taken? Sorry? This is for the common mode half circuit. Let's say this is the first stage. It connects to the second stage here. And where is the output taken from? From here. That's where the feedback is complete. Okay. So I'll have to connect my capacitor between this input and this output. Okay. So you'll have to go and put a capacitor like this. I have two outputs here, so I have to do like this. Okay. Now there is one other variant that is commonly used, it's minor variation. So you can also add one more current source transistor here. Okay, and set the bias current independently. Okay. So this way even the second GM is biased with a constant current, and that will have a good common mode rejection. Okay. So note that whenever you have biased a particular GM with a constant current, it is going to have a good common mode rejection. Okay. So in this case, my first stage GM is biased with a constant current. It will have a good common mode rejection. Now my third stage, that is also biased with a constant current. So we can also have a similar configuration for the second stage also. This is also very commonly done. And the moment you have it, now the current of the second stage is controlled by this PMOS transistor. So for common mode feedback, you can also control this guy. That is, you can fix the bottom current constant and control the top current. Okay. So just I'll make a couple of points more on common mode thing. See, as we saw, in a fully differential system, we need to have a good common mode rejection. Okay, but let's say you have a cascade of multiple systems. It is not necessary that all stages must have a common mode rejection. Even if, let us say, the first stage, this guy has a good CMRR. In that case, if there is a common mode change, my outputs are not going to be disturbed. So here I can have a pseudo differential configuration like this. That is, this is my second stage now, right? It is not necessary that all the stages should have a common mode rejection. One of these stages, preferably the first stage, if it has a common mode rejection, that's good enough. And if you think carefully, that is the reason why for the Miller's OTA, where is the, yeah, in the two-stage Miller OTA here, this is the first stage. So because of this tail transistor, it is having a good common mode rejection. Now the second stage is implemented as two amplifiers like this in a pseudo differential manner, right? Because these are two amps operating independently. So this is okay here because the first stage here is having a good common mode rejection. Okay. Whereas in the feedforward case, that was a problem because the third stage here, that was directly connected to the output. So that was killing our common mode performance. So that is why here this also needed to be having a good common mode rejection because it is directly processing the input. But otherwise, it is okay even if the first stage has a good common mode rejection. So there is one other interesting thing this common mode feedback loop does. So let me show that. So say I take a pseudo differential amplifier like this. This is a pseudo differential configuration where we have two separate amplifiers, that's all. Okay, this is biased to some current. Now let us say I have a common mode feedback here and set this current to some. Okay, I am setting the common mode to some VCM ref. Okay. Now let us say there is some common mode jump at the input. I know that both the outputs will respond in the same way, right? So what do you think in steady state, what do you think the output common mode will settle to? VCM ref, right? Or I explicitly show that, see. So let us say I take the two outputs like this, average it, compare it to some VCM ref. This is my CMFB, right? So now if I apply a common mode step here, I know that my outputs will respond in the same way, but this negative feedback loop is setting it equal to a constant value, right? So what can you say about the common mode gain here? Zero, right? I am applying a common mode step, but I find that my output common mode is not changing and it is set to this value of VCM ref. Okay, so here you see that the common mode gain becomes 0. That is because of this negative feedback loop, which is separately trying to make sure that the common mode is not changing. Okay, so the way it is doing is it is trying to make sure that the output impedance in the common mode half circuit is very small. Okay, so to understand it, let me take a different example because this is what I have asked in your assignment. See, I will take the same pseudo differential amp. I will use a simplistic common mode feedback like this. Okay, so this is the pseudo differential. So if I draw the common mode half circuit, I will have this guy, I will have this guy. So what will happen to the resistor? That will be in feedback like this. Now this is the common mode. In the differential mode, how is the circuit looking like? I have the PMOS and NMOS. What is happening to the gate of the MOSFET? That is incrementally ground because this is all ground. And then I have the resistor also connected. So what is the output impedance here? R out common mode. This is the impedance looking here. What do you think that is? I mean, when I have this, what is the impedance? 1 by GM. So if I have a resistor, what happens now? Can there be a current flow here in this direction?
No.
It's a gate, right? There cannot be a current flow. So having a resistor or not doesn't make a difference. So what is the impedance now? 1 by GM, right? Because see, whatever voltage I apply here, the same voltage will come here. Okay. So common mode output impedance is 1 by GM. Parallel with the R0, but it's 1 by GM. So here what is the output impedance in the differential mode? Yeah, it's RCM parallel with the two output resistances. So let us say RCM is large enough, that is basically this guy. Okay. But if you didn't have this guy at all, if you didn't have this common mode feedback, you will not have this thing. Then both my common mode and differential mode output resistance will be same. Right? The moment I added the common mode feedback, it is reducing my output resistance for the common mode signals. If the output resistance decreases for common mode, what can you say about the common mode gain? That will also reduce. That is why you see that the common mode feedback is also giving you making sure the common mode gain is small. And in this case, if let us say this amplifier has infinite gain, then the common mode is set to one value of VCM ref. So here, what do you think is the output resistance in common mode? The output common mode is not changing, it is set to one constant value of VCM ref. So what is the output?
Infinite.
No, it cannot be infinite. It has to be? Why is it 0?
Any change in current is not giving is 0.
No, not DA is not 0. What is 0?
Sir, it is.
See, the output common mode is fixed to one value. So it is as though it is like a voltage source setting the value to something. So then what is the resistance here? 0. I mean, it is as though you put a voltage source and fixing this to VCM ref, right? So here the output resistance in the common mode picture is 0. And remember, all this is possible because this amplifier is tweaking this gate voltage here to keep my output common mode to be fixed. Okay. And I mean, with infinite output resistance it is 0. With infinite gain the output resistance is 0. With finite gain it will be a small number. Okay. But there is one catch. So here let us say again, as usual, I apply a common mode step here. Push it here. Before applying the step, the output common mode was set to some VCM ref. Okay. Now I apply a step here. If the amplifier is infinitely fast, it will respond instantly and keep the value constant. Okay. But we know that the amplifier will have some finite omega u, will have some capacitors. So at the time instant where the step is applied, this guy will not be active. Right, because this will take some time to respond. At the instant where you have applied the step, this common mode feedback loop will not be active. The time is called, is it? Okay. Oh, so I didn't know. Sorry. Here, yeah. Bell didn't ring. Huh? So you have a class, you leave. You have a class?
Yeah.
Huh?
No class, but
Oh, I didn't realize the bell rang. Sorry. Bell. Sorry. If someone has class, you can leave. Else I'll just finish this couple of minutes. So what I'm getting is, if you apply a common mode step here, if this common mode feedback loop is infinitely fast, it will respond and keep it constant. But you know that this is going to have some finite omega u and it will have its own capacitors and stuff. So in that case, at the time instant where this step is applied, this guy is not active at all. Right? So if this is not active, if I apply common mode jump of delta Vc, what can you say about the currents here? Incremental currents. It's Gm delta Vc. So this current will flow into the output resistance here. And as I mentioned, at t equal to 0 plus, the common mode feedback loop is not active. So in that case, what is the output resistance?
R0.
It is going to be the R0 of the two transistors in parallel, because the feedback loop is not active yet. So this current will flow into this large output resistance, and of course let's say you have a capacitor also here. So the output will try to increase or decrease slowly. So let's say it's increasing in this case. I mean, if we don't have this common mode feedback loop at all, the output will go and do this. Okay, but now we have this common mode feedback loop. So what will happen is this. So it will do this. At this point, the common mode feedback loop will start to respond. So it will do something like this. Okay, or it might do some ringing also. I mean, I don't know. Depends on the phase margin of your common mode feedback loop. Okay. Yeah. So the issue, I mean, the point is, it is not good enough to have just this common mode feedback loop. because this common mode feedback loop is taking some time to set my output common mode to something. Okay, so it is not good enough to rely on the common mode rejection provided by the CMFB alone. Okay, because for example, if I had a proper current source here, I know that even if there is a sudden jump in the input, the current here will be 0, right? Because this guy is fixing the current to some constant. Even if there is a jump in the common mode input, the incremental current is 0. Okay, so in that case, the output will not even change, it will just simply stay like this. So the CMFB, we just remark it and finish. It sets the output DC bias, and it also gives some common mode rejection. But it is not always good enough to just rely on this common mode rejection, because the CMFB will take some time to settle. Okay, so it is always good to have a common mode rejection provided by a tail current source. And the speed of this thing, what does it depend on? Omega u of the common mode loop. Okay, so usually you have omega u for the common mode loop, and we also will have for the differential mode some omega u. Usually you want both of them to be of the same order. Okay, but in practice, if you want to keep both to be same, you'll have to burn more power in the common mode feedback loop. So we try to keep it slightly smaller. So we'll stop here.